Welcome to this episode of Mentors At Your Benchside, the podcast giving you advice, tips and tools for getting the most out of your research. I'm Thomas Warwick, and today I'll be talking to you about the chemicals you can use past their expiry date and the ones you cannot. Have you ever picked a chemical that's years out of date up off the shelf and wondered, can I still use this? Chemicals are expensive. Most labs contain thousands, and few people in the lab know which are in date and which aren't. Replacing them whenever they go out of date is a massive waste of grant money. Plus, we use some chemicals so rarely, and it's also rare that people sort out their benches before leaving. The result is a pile-up of old chemicals and solutions, some potentially useful and worth keeping. So what reagents are useful past their chemical expiry date? How do you check if they're still okay, and which ones should you throw out? Let's go through some different types of reagents and see what you can use and which ones you should throw away. Buffers. In the lab, you'll encounter buffer solutions, e.g. 1 molar Tristox, and buffer salts, e.g. sodium citrate. Buffer salts should be fine to use past their expiry date since they're usually stable, unreactive solids. As long as they've been stored in the original container, you should be good to go. Buffer solutions are different, and you should probably throw them out. This is because they're usually pH adjusted to somewhere around physiological pH. Consider also that buffer molecules and their breakdown products and molecules dissolved in the air can provide carbon and nitrogen sources, and you have ideal growth conditions for unwanted bacteria and fungus. These can change the pH of the solution away from the one written on the bottle. Swirl your buffer solutions occasionally and look for floaty bits to check if anything is growing in them. In a pinch, you could filter sterilize your buffer solutions to remove anything that has grown before reusing them. Just check the pH is still correct. General salts. Most of the chemicals on your shelf will be salts of some sort, like magnesium chloride, potassium phosphate, and calcium carbonate. Like buffer crystals, many of these salts in your lab are unreactive solids and okay to use beyond their expiry date. Just beware that some salts are hygroscopic. They attract atmospheric water, sometimes so much so that they get physically wet. Examples of hygroscopic salts include zinc chloride and calcium chloride. Plus, simple salts are relatively cheap, meaning we buy them in huge tubs that sit around for years. You'll find out which salts are hygroscopic when you come to open them and they're soaking wet. Throw these out because you can't weigh them out accurately, meaning there'll be an error in the molarity of your solutions. In a pinch, you could try drying them out by freeze drying them or warming them up gently in low humidity conditions. Reducing agents. Let's split these into two. BME and DTT. Beta-mercaptoethanol, BME, is a liquid at room temperature, and dithiothietol, DTT, is a white solid at room temperature. Avoid reusing solutions that contain them, and add them immediately before your experiments. Depending on the pH and temperature of the solution, their half-life is between a few hours and several days. Pure BME and DTT are stable for 1 to 3 years if stored properly. You're likely to finish the bottle before it goes out of date. Don't use them beyond their shelf life, because if they've lost their potency, it will give you a real headache when you come to troubleshoot what's gone wrong. TSEP. Tris-2-carboxyethyl phosphine, or TSEP, is a solid at room temperature and more stable in aqueous solutions than BME and DTT. The powder is stable and should be okay to use beyond its expiry date. Solutions of it are more stable than BME and DTT, but they don't last forever. Discard them after a month or freeze them down at -20 degrees centigrade. How to qualitatively check if reducing agents still work. Find a sample of a protein in your lab containing 2 or more peptide chains held together by disulfide bonds and run an sds-page gel of it. Antibodies work great, but check to see if you have something cheaper to hand. Run one gel with a sample containing 1 to 10 millimolar reducing agent, and run another gel with no reducing agent in the sample. If the reducing agent is okay, it will break the disulfide bonds, resulting in more bands on your gel corresponding to the individual protein chains. The unreduced sample will produce a single heavier band corresponding to the disulfide link chains. And finally, because they lose potency quickly, reducing agents are one of the first things to check when things go unexpectedly wrong in your experiments. Phenyl methyl sulfonyl fluoride. Phenyl methyl sulfonyl fluoride, or PMSF, is a common serine protease inhibitor. The powder is okay to use past its expiry date, unless you notice your sample starts getting proteolyzed. If this happens, buy some new PMSF. Aqueous solutions of PMSF have a half-life of around 30 minutes, so don't reuse them. And stock solutions of PMSF are usually prepared at 100 millimolar in isopropanol. These should be stable for several months at 4 degrees centigrade or several years at -20 degrees centigrade. Heavy metal salts include chemicals like nickel sulfate, cobalt chloride, silver nitrate and gold chloride. These stable compounds last almost indefinitely and can be used well beyond their shelf life. Spillage and contamination are more likely to ruin them before they become chemically unsuitable for your experiments. Ditto for solutions. Heavy metals are antiseptic. Nothing should grow in gold, silver, cobalt and nickel solutions, so you can keep them for years on your shelf. Antibiotics. Generally, use the powders regardless of how old they are, but don't use old solutions. A few points to note. Generally speaking, crystals are unreactive solids. That's why it doesn't matter if they're old. However, once dissolved in solution, some will doubtless be more stable than others. Now, there are a lot of antibiotics we can use in research, and I don't know the chemistry of most of them. Plus, they will have different stabilities depending on what they're dissolved in and how they have been stored. Finally, antibiotics are usually a critical component of our experiments. That's why it's best to err on the side of caution with solutions. Ammonium persulfate. Desiccated ammonium persulfate is stable and will last for years, so you can use the really old stuff in your lab. However, ammonium persulfate hydrolyzes rapidly in solution, producing ammonium hydrogen sulfate and hydrogen peroxide, so never use old ammonium persulfate solutions. Hydrogen peroxide. Hydrogen peroxide is okay to use past its chemical expiry date if stored in the dark. The liquid, supplied as a 30% weight by volume solution, is stable but decomposes when exposed to light, so factor this into your decision. For this reason, and because reagent bottles are usually transparent, old working solutions that contain dilute hydrogen peroxide should be discarded. How to qualitatively check whether hydrogen peroxide is still usable. Hydrogen peroxide oxidizes potassium iodide, forming iodine, potassium hydroxide, and hydrogen gas. Aqueous solutions of potassium iodide are clear, but iodine solutions are brown. Thus, if you prepare 100 mmol of potassium iodide, add a few drops of hydrogen peroxide into it, and it slowly turns brown, the hydrogen peroxide still works. Sodium dodecyl sulfate. Sodium dodecyl sulfate, or SDS powders, and solutions should be fine to use beyond their use-by date. Sometimes sodium dodecyl sulfate may precipitate out of solution, especially when it gets cold in the lab. If this happens, heat the solution gently on a hot plate while stirring and cover the bottle in tin foil to keep the heat in. Sugars. Old powders should be fine to use, but check solutions for growth. Like most chemicals on this list, and in general, the crystals are stable, unreactive solids. Sugar solutions are similarly stable, but the molecules are high-energy food sources for microbes. Add the fact that sugar solutions will be at or near neutral pH, and this is why things start growing in them really quickly. Be sure to check old solutions for contamination before using them. For a summary of everything we've discussed so far, check out the table in the corresponding online article. Before discarding a reagent out of superstition, think about its chemistry. For example, is it composed of strong ionic bonds? Can it oxidize? Is it photosensitive? Does it degrade in water? And might its composition have changed? Before using old chemicals and solutions, consider their biochemistry. Things like, what properties make it useful? Is it a nitrogen source? Is it a carbon source? Is it antiseptic? Will it retain selectivity? So there's your list of common chemicals and whether or not they're okay to use past their chemical expiry date, and how to check if they're still good. Plus a bit of chemistry to help you understand why some old reagents still work. Hopefully you can apply this wisdom to chemicals in your lab to help you decide on a case-by-case basis. Using old reagents can save you time, waiting for orders, and money otherwise spent on them. Note that these aren't hard and fast rules. I've based what I've written on the accumulation of my lab experience. You can take this advice as generally or literally as you wish. For sensitive and critical experiments, try using the freshest reagents to avoid a heavy heart if things go wrong. So that's it for which chemicals you can use past their expiry date. Check out the episode description for links to related articles and resources, and don't forget to subscribe to the podcast to get more help and advice from mentors at your bench.